time for part 3 of chapter 14. So this is going to go more into some of the functions of the brain. So looking at the different patterns that we use with the coding of our brain information, so our brain waves, that also will be shown in the stages of our sleep. So that's how we know the different stages of sleep. And then different brain region functions like motion, memory, motor control, as well as language. So in order to look at the brain frequency of action potentials and activity that's going on in the brain, we use a measurement called a electroencephalogram, or EEG for short. So we're able to see the electrical activity of what's going on in the brain, and depending on what state you're in is going to determine the function of your brain. So for example, right now, as you're learning, you should at a minimum be at a frequency of 10 hertz per minute. Preferably 60 hertz per minute, because that's where you're in the learning function. So high brain activity, high alertness, able to process information and able to store it. So you're in the learning phase. We're able to also use these to look at levels of sleep, so our different stages, looking at normal functions, so comparing a normal clinical study participant's activity to someone who is a patient in that study receiving some type of treatment. So you're able to see the differences in their brain activity. So for example, people who have ringing in the ears, they tend to have lower brain activity in the temporal lobe, that's for hearing, than a person who doesn't suffer from tinnitus all the time. And that's just a difference in activity, or that information coming in because they've had some nerve damage typically, and so their brain activity goes down, and that's why the brain just starts making up stuff, because it's used to having a certain level of activity because it's always hearing stuff. So if you ever heard someone being called brain dead, it's because they have done the EEG and realized that there is no activity going on in the brain. So with our activity, they have different levels, so different frequencies. So alpha is when you're awake, beta is when your eyes, alpha when your eyes are closed but still awake, beta, which is a little bit faster when your eyes are open, so you're getting extra sensory information in, so you have faster processing at that moment. Theta waves is when you're slowing down and getting drowsy, and then delta waves, which is seen in adult people when you're in deep sleep. Okay, so this is looking at different types of EEG setups. So what Colbert is wearing, it's a 64 channel cap. So each spot on there is showing kind of the generic activity in that area. So moving on to the little baby's cap, it's a different type of cap, also different method of making the connection with the brain. So you're able to record the electroactivity. In that type, you're still using a salt solution to make the connection. However, you have way more electrodes. This one should be 128 electrodes, so you're getting more specific information on the activity. So why do we care? This is why we care. So with our body taking in information and having our activity of the brain, it is affected by our circadian rhythms. So part of it is hormones, so from our pituitary gland, some of it's from our bringing in of light. So that's why even people who are night shift workers and they sleep during the day and they have the blackout curtain so they can kind of pretend that it's night and help to trick their body that it is nighttime and they'll actually sleep. So here's our normal circadian rhythms. So our need for sleep kind of slows. This is when we're actually sleeping at nighttime when it's still dark outside, but then sun comes up. And our need for sleep, not much. It does increase in the day, so eventually we get tired, and eventually by the time after it gets dark a little bit and we kind of get that signal of, hey, it's nighttime, it'd be a good time to sleep now. So we do have this little bump in the middle of the day. This is why around 2 o'clock you have that kind of urge for, I need a coffee, I need some caffeine, I need to take a nap. It's because of this. You have this weird little bump of need for sleep, kind of like a break during the middle of the day. So that's why in some countries they have like a siesta, or you have afternoon tea. It's just a break during that time so that you can kind of replenish and get along with your day for the rest of it. So sleep is defined as a temporary state of unconsciousness, and then you actually can be stimulated to wake up versus someone who's like in a coma. When you sleep, our body undergoes sleep paralysis, so we have an inhibition of muscular activity. So this is where you don't act out your dreams, so you don't accidentally smack your partner because you're moving around, or so you don't accidentally roll off the bed because you're moving around. Some animals don't have this. For example, if you've ever seen a dog that's sleeping, you see the cute little videos where his legs are kicking because he's running in the middle of a field in his dream. That's where you don't have that sleep paralysis. So the dog is actually acting out its dream. So in sleep, we have 4 different stages. So each of these 4 stages have different frequency patterns, which we actually can record on that EEG and determine how deep sleep you have. You go through these different stages, you pop back up through stage 2, which is our dream or rapid eye movement sleep. So this can resemble being awake just because you're active and doing stuff in your dream. You do have more sleep paralysis, so you don't, again, knock out your partner because you're, doing something in your dream. So helping to regulate this is the suprachiasmatic nucleus. So going back to our brain, and we haven't talked about this yet. Okay, I just realized that. So part of, and I mentioned this earlier, those nerves, the cranial nerves that extend off of your brain stem, one of them is your optic nerve. So they're receiving the sensory information from your eyes. Part of its ability to do its job is that it crosses. So you're getting information from both eyes. Your brain compares both sides, and that helps you to see in 3D. Where this crosses, you have this nucleus that is above it, so superior to that chiasm or that X crossing. So it's going to get a little bit of that visual information that helps your body know what time of day it is. So obviously it's going to be brighter at noon than it was in the morning, and same thing, it gets darker at night. So it helps with our body's normal circadian rhythms, knowing what time of day it is. So this is why, for example, some people, when it comes to their office light, or if they're at home, if it's in the evening time, they'll switch to a lamp instead of bright overhead lights, which give the visual signal that it is noontime when actually it's not. Okay. So part of that light level is also looking at the angle of where your light is coming from. So that suprachiasmatic nucleus is taking in that visual information to determine what time of day it is. So you also have other areas of the brain that are going to affect your sleep. Main purpose of sleep is to kind of help restore the body. So able to do some healing and repair. This is why sleep deprivation is sometimes used as a torture technique, because without sleep you can actually cause someone to die because they need that restoration from the sleep. It also can help consolidate and strengthen memories. So, for example, as you're studying for your exam, studying as you go along helps because you're getting sleep in between the days as you're going along, just preferably not in my class. However, this is a whole lot better than trying to cram and you only have a night or two in order to get that sleep to create those good memory connections. So studying over time is going to be helpful. All right, let's look at what our different brain regions actually do. So first function of the brain is cognition. So we have three different lobes, that help with cognition. So the first one, the parietal lobe, its job is to perceive and attend to stimuli. So the sensory information coming into the brain. So reason why we're able to know what these different areas do is because we've had patients who've had lesions or some kind of damage in those areas, and because they had damage, they stop having certain functions. So this is how we actually figured out what these areas do. So a lesion in this area leads to contralateral neglect syndrome. So I'll show you examples of all of these later. Temporal lobe also helps to identify stimuli, so not just perceive that it's there, but also figure out what the heck it is. So a lesion or damage can lead to agnosia, so inability to recognize something. Next one, frontal lobe. So this allows us to think about the world, help to make good plans, execute appropriate behaviors, so making our good judgment, making good social behaviors. So a lesion or damage in there leads to personality disorders as well as socially inappropriate behaviors. So here are examples. So this one is contralateral neglect. So in this first section, we have a picture of a house. The patient who has a lesion in the right parietal lobe is going to ignore stuff that's on the contralateral because our information is going to cross over or decussate into the opposite side of the brain. So our right side of the brain controls and receives information from the left side. Our left side of the brain controls and receives information from the right side of the brain. So it's the opposite side of where you're getting your information and receiving. Anyway, so lesions on the right, they neglect stuff that's on the left. So if they're looking at this house, they're going to ignore the left side of the house in this drawing. So when their job is to copy that house, they're only going to draw the right side because they ignore the left side. Down here, same situation. The patient ignores the left side of the plate, so they'll only eat what's on the right side. So in order to get them to finish their plate, you just turn the plate around and then they'll be like, oh, food. And they'll actually recognize that it's there. Sometimes some people also have the same situation where they stop recognizing the left and right sides of their body. So they'll have what they'll do is they'll put a mirror in between, for example, their arms, and they'll have them move for example, this would be the right arm, and they'll have it move and they'll see the mirror having that same image, and that helps them to recognize the other part of their body, as in, oh yeah, there is another side to me. Another defect due to a frontal lobe lesion, and if you are in psychology or eventually take it, you'll hear about this dude. His name is Phineas Gage. And the only reason why we know his name is just because this happened before we had all these HIPAA regulations where you have to keep patient information safe and not tell everybody what's going on with the patients. So we know his full name. So sometimes you'll see stuff where it's just the initials, and now everything is coded and everything. But yeah, this is old enough where we get your whole name. Okay, so frontal lobe lesion. So the guy in the picture used to work for the railroad, doing different explosion, demolition kind of stuff. Well, the rod he's holding in his hand, it was part of that. It was a railroad spike. The explosion went off before it was supposed to, and he was actually in the middle of checking it when it went through his left eye and part of his frontal lobe. So he went from being like a model citizen to being reckless with socially inappropriate behavior. So what helped him though, is because he needed something that's structured and keeping a schedule. He ended up becoming a stagecoach driver, so that schedule helped to keep him organized, as well as because he wasn't making appropriate behaviors, as in thinking, oh, driving this sucker too fast, that's probably not a good idea. Well, he would drive the stagecoach too fast, and he would definitely make his time. And that actually made him a little famous. So it's kind of like NASCAR before NASCAR happened, because seeing him drive so fast, because most normal people wouldn't do that. Okay, next function is memory. So memory isn't actually stored in a particular place. It's just a pattern of neuron firing. That is when you get that sensor information triggered, or you're thinking about something and it eventually gets that pattern going, then you're able to bring up that memory. So with our memory, we learn something new, we eventually store it, and then sometimes we forget. So for example, your breakfast from yesterday, you probably don't remember what you had unless you have the exact same thing every day. So some stuff is forgotten because your brain is like, oh, well, we haven't talked about this in a while, so I'm going to ignore it. So, for example, some of your AP1 material, depending on when you take AP2, you definitely might want to kind of look over stuff before you take the next section because you're going to start forgetting stuff. Even just preparing for the final exam, reviewing occasionally so that you have that stuff fresh. There's also a study guide for your final exam, by the way. And it's based off of the study guides that you've already complete. So each of your previous one, exam 1, 2, 3, those study guides, it actually refers to, hey, for this question, you need the answer from that one. So it's the exact same question. So if you've done the study guides, you're in good shape. Okay. So if we have a defect, sorry for the random tangent, a defect in memory that's called amnesia. So there's two different types of amnesia. We have anterograde, so unable to store new information. Retrograde is forgetting stuff that happened before our injury. Well, not our injury, before the patient's injury. There we go. That's a lot better. So one part of our brain that's really important in memory is the hippocampus. So it allows us to consolidate our memory. So take stuff that was short-term learned and actually put it into storage. Again, the memory isn't stored in the hippocampus, but the hippocampus is necessary in order to get the short-term memory into long-term. Again, back to earlier when we talked about what happens when we had damage and then someone loses the function. Oh, we found out what this part does. So going back to our patient, now we have a little bit more patient privacy, so we're dealing with initials now. So this patient, initialed HM, had surgery to remove both of their hippocampi, so both hippocampus on each side. And this got rid of his ability to form new memories. So he could remember stuff from the past, because those are already in long-term storage, but because he no longer had his hippocampus, he could no longer create new memories. Oh well. Okay. Other things that are important in memory, cerebellum, so helping us with motor skills. So for example, you tying your shoe, you can do that very easily because that motor plan's always there and you don't really have to think about how to tie your shoe. Your amygdala is also part of emotional memory. So tying the emotions to a memory as part of that whole experience. Speaking of emotion, let's move to that function. So for our emotions, we have different parts that affect that. One would be our prefrontal cortex. So when it comes to expressing emotions, especially if your brain has been fully developed, it's a whole lot easier to express your emotions in a socially appropriate manner. So for example, someone at your job that irritates the crap out of you, well, it might take a little work for your brain to not go off on that person. That's what that frontal cortex is going to do. It's going to help keep that in, or if you're having to write an email to someone and try to be all professional, that frontal cortex is helping you to be professional when you really want to really go at that person. Okay. Other parts, we have the hypothalamus helping with our coordinate with their different hormones that are related to emotion. So that's going to affect different parts of the body because the hormones circulate through your bloodstream. And also your amygdala. So that is your big portion of your limbic system that takes sensory information in and then can send output to your body system. So for example, if you're super excited, your heart will start to race, your blood pressure goes up. So this is going to be a part of that emotional response. Same thing, put output to the prefrontal cortex, and that way your prefrontal cortex can kind of adjust what you're feeling and help you express it appropriately. Okay, so this next section deals with senses. I'm actually going to start a new video. Yes, there's 4 videos for chapter 14, but it's also a major chunk of your exam. See ya.